Good morning, welcome to new lecture. Today I will talk about stress transformations. So, new topic, we will talk about stress transformations. What does that mean, stress transformations? For example, assume we have one part, something like this. Of course, we can have hundreds of examples in real life, but assume we have one part, something like this. Cross-sectional area for this part, you see, it is circular or cylindrical shape, and this part is subjected to tension force in this direction, tension force in this direction, and torque in this direction, and another torque and torque in this direction. Assume we have one part. In real life, I can give you hundreds of examples, but here it is easy example to imagine. We have one part, there are two rods or two cylinders perpendicular to each other. We apply tension in this direction, tension in vertical direction. We apply torque and torque. Let's look at one small element on the surface of this part. This is small element. If we look at the stress on this small element, what we will have? Because of this tension force, tension divided by cross-sectional area, we will have tensile stress. Sigma x and sigma x. This is my x direction, this is my y direction. Because of this force in vertical direction, I have force divided by cross-sectional area, assume sigma y, sigma y. This torque will produce shear stress. Shear stress will be tangent to here. That will be tau xy. And in this side, we will have tau xy again in inverse direction. Because this element should be in equilibrium, in horizontal direction, vertical direction. This sigma x and this sigma x, they will cancel each other, sigma y and sigma y, tau x and tau xy and tau xy. And this torque will produce tau yx and tau yx. Let's first explain how we will name this. If this is x direction, this is y direction, this surface perpendicular to the x direction, we will call it x, face of element. So, these two faces are perpendicular to the x direction, we will call it x face of element. On x face, normal stress, in the x direction, we will call it sigma x. This face and this face, these two faces are perpendicular to the y direction. We will call it y face of element. In y face of element, normal stress parallel to the y direction or in y direction, we will call it sigma y and sigma y. Sigma always will represent normal stress. We will have two types of stress always, normal and shear. Normal stress, it is sigma perpendicular to the surface. shear stress tau tangent to the surface. Why we call this tau xy? Tau xy means, tau means it is shear stress, it is tangent to the surface. X means it is on x face of element. Y means it is in the y direction. Why we call this tau yx? Tau, it means it is shear stress. Y means it is on y face of element. X means it is in x direction. So this is the way we will name these stress components. And after naming this stress component, we should pay attention. This is plane stress element. Plane stress elements means this element has two dimensions. It is in 2D plane. Stress component in the z direction. This is x, this is y. For example, this is z. Stress in the z direction, it is equal to the 0. Stress for here, we don't have any stress in the z direction. And our element, it is in 2D plane. And stress, normal stress, in the z direction is equal to the 0. For that reason, we will call it plane stress element or 2D element. So, in the plane stress element, the stress component perpendicular to this board, it is equal to 0, or perpendicular to this face, it is equal to 0. Now, this element will be subjected to these stress components. These stress components, how we will combine this? Because this stress component, if we combine together, can cause maybe bigger stress, and that will result failure. But how we will combine this component? How we will combine stress component? We cannot just simply add together. We cannot do that. In order to combine these stress components, we need stress transformation. I will explain what is the stress transformation and how we will do that. Assume in one inclined direction, if I show that inclined direction, theta, if I cut this element in inclined direction such as theta, now the stress element, instead of square shape, will have a triangle shape. Here we have sigma y, tau yx, tau xy, and sigma x. On this inclined surface, we will have again one normal stress, I show with sigma theta, and one shear stress. Shear stress I will show with tau theta. Pay attention, these stress components are independent, but always tau xy is equal to tau yx. Why? Because in order to keep this stress element in equilibrium, it should not move in vertical direction, it should not move in horizontal direction, and it should not rotate. Because it should not rotate, if we take moment respect, for example, to the center of this element, from that we can find tau xy should be equal to tau yx. Because in order to satisfy summation of moment is equal to 0, this component should be equal. So always tau xy should be equal to tau yx. Otherwise, this element will start to rotate. And in order to prevent rotation, tau xy should be equal to tau yx. You can take moment respect to the center point. You will see, you will end up with this relationship. Anyway, usually tensile stress outward, we will assume it is positive, and shear stress, if rotate this plane counterclockwise, we will assume it is positive. You see here, this shear component, it rotates counterclockwise, this element. So we will assume it is positive direction. That is contract. So here I will follow that contract. Let's look at to this element. I cut this element with one inclined plane, and that angle is theta. If that angle is theta, and this is x direction, this is y direction, perpendicular to that inclined plane, if I call, for example, this is n direction and this is t direction, this angle will be theta as well, and this angle again will be theta. From geometry, we know that. If I look at to this element in 3 dimension, in 2 dimension, it is like this. Here, the length, if it is h, I assume, this is theta. This side of triangle will be h cosine theta, and this side of the triangle will be sine theta, h sine theta. So we have each side of triangle. This side, I assume it is h. If this angle is theta, this length will be h cosine theta, this length will be h sine theta. And in 3 dimension, finally, this element has thickness. If I show the thickness of element with T, so the area, for example, this face area will be length h times T will be this area. And we have other area we can find. In order to have this element in equilibrium, in order to satisfy equilibrium condition, again, summation of forces in x direction should be equal to 0, and summation of forces in y direction should be equal to 0. If I write that summation of forces, let's see what will happen. I will draw that picture one more time, and I will write summation of forces in the x and y direction. Okay. Here, again, stress element, theta, sigma theta, tau theta, tau xy, sigma y, sigma x, tau y x, x direction, y direction, and perpendicular to this surface, t tangent to the surface, this is theta, and dimension h cosine theta, because this angle is theta, h sine theta. If I write summation of forces in x and direction is equal to 0, and summation of forces in y direction is equal to 0. Let's see what we will have. And you know how we can find the force stress times area will give us the force. And in order to have area, we will need the length of each side times the thickness perpendicular to the board. I assume the thickness it is T. So summation of forces in the x direction is equal to minus sigma x T at cosine theta minus tau xy T at sine theta plus sigma theta cosine theta T at minus tau theta sine theta T at is equal to 0 in the x direction. In the x direction, sigma x it is in negative, sigma x times h cosine theta times t minus tau xy times h sine theta times t sigma y times h times t cosine theta minus, if we project this tau theta, it will be directed from right to left, it will be negative direction. Tau theta times h times t times sine theta is equal to 0. Another equilibrium equation, it will be summation of forces in y direction is equal to 0. Summation of forces in y direction will be equal to minus tau xy t at cosine theta minus sigma y t at sine theta plus sigma theta sine theta t at plus tau theta cosine theta t at is equal to 0. So after putting this equation, we can combine this equation. If we multiply both sides of summation of forces in the x direction with cosine theta and the y direction with sine theta, and we combine like this, if we combine like this, summation of forces in x times cosine theta plus summation of force in y times sine theta is equal to 0. We will multiply entire this equation both sides to the cosine theta, and we will multiply both sides of this equation to the sine theta, and we will add together another combination minus summation of fx sine theta plus summation of forces in the y direction cosine theta. So we will multiply both sides of this equation with negative sine theta, both sides of this equation with cosine theta, and we will add together. If we combine this like this, and if we cancel those terms, they are similar, they are identical, but one of them is positive, another negative. After simplification, we will have this equation. We will end up with stress, normal stress in this inclined plane is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine 2 theta plus tau x y sine 2 theta, and shear stress in this inclined plane tau theta will be equal to tau xy cosine 2 theta plus sigma y minus sigma x over 2 times sine 2 theta. So we will end up with these two equations. So if we have sigma x, sigma y and tau xy in any inclined plane, such as inclined plane theta, we can find normal stress and shear stress. Let's see how we can find maximum normal stress, minimum normal stress, and maximum shear stress. In which plane, in which inclined plane we will have maximum normal stress, in which inclined plane we will have minimum normal stress, and in which inclined plane, in which theta we will have maximum shear stress. Theta can have any number, infinite number. Theta can be 1 degree, 2 degree, 3 degree, any number, okay? Theta can have any number. But only in one theta, theta is equal to a certain value, normal stress will be maximum or minimum shear stress will be maximum. And what is that theta? How we can find that theta? In order to find that theta, we can take derivative of tau theta respect to the theta, and we will put equal to the 0. In order to find that theta for normal stress, we can take derivative of sigma theta respect to the theta equal to 0. That will give us that theta. Then if we come back and substitute that theta in this equation, we will find the maximum value for normal stress or minimum value for normal stress and maximum value for shear stress. But before doing that, let's look at this formula. If here, in this equation, if in these equations, if we put theta is equal to 0, in theta is equal to 0, if you plug theta is equal to here, you will see sigma theta will be equal to the sigma x, and tau theta will be tau xy, which is right, theta equal to 0 value. If we plug theta is equal to 90 degree, you will see sigma 90 will be equal to sigma y, and tau 90 will be equal to minus tau x y. Again, theta 90, theta is equal to 90 degree, it is right. So these two formula are right. They give right values. Now let's look at today how we can find the maximum shear stress and then normal stress. If we calculate d tau theta respect to d theta, that will be equal to derivative of tau xy cosine 2 theta plus sigma y minus sigma x over 2 sine 2 theta respect to the theta equal to 0. If we calculate this, you can take derivative, you will see it is minus 2 tau xy sine 2 theta plus sigma y minus sigma x cosine 2 theta is equal to 0. From here, if I take to other side, I can write sine 2 theta over cosine 2 theta is equal to tangent 2 theta, which is equal to sigma y minus sigma x divided by 2 tau xy. Because this theta will give us the maximum value for shear stress, I show that with theta and this s. So tangent to theta and this s is equal to sigma y minus sigma x divided by 2 over tau xy. So if we have one triangle this is tau xy, this is sigma y minus sigma x over 2. This length, I assume it is capital H. From here, capital H length, I can find it. It will be sigma y minus sigma x over 2 squared plus tau xy squared. And if this angle is, I call this angle 2 theta s, in that case cosine 2 theta s will be equal to, here cosine 2 theta s will be tau xy over h, and sine 2 theta s will be equal to sigma y minus sigma x over 2 divided by h. Because tau theta was equal to tau xy cosine 2 theta plus 1 over 2 sigma y minus sigma x sine 2 theta. For maximum angle, this will be theta s, and here you can plug, instead of cosine 2 theta s, tau xy over h, instead of sine 2 theta s, you can plug sigma y minus sigma x over 2 over h. If you do that, you will end up here. This will be equal to tau xy squared over capital H plus sigma y minus sigma x over 2 squared over h. From here, if instead of h I plug this term, we have here, you will plug here and here instead of h, and if you simplify that, finally you will end up with this term. You will end up with maximum shear stress theta s will be equal to square root of tau y minus tau x over 2 squared plus tau xy squared. And we know how we can find theta s tangent to theta s is equal to sigma y minus sigma x over 2 tau xy. So we can find orientation of that plane. We will have maximum shear stress using this formula. We will plug here and we will find the maximum shear stress in that plane. Let's look at the normal stress to see what we can do in order to find the maximum normal stress. Maximum normal stress, we should do similar thing. We should put derivative of normal stress respect to theta is equal to 0. That will be derivative of sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine 2 theta plus tau x y sine 2 theta. If we take derivative of this respect to the theta, that will be equal to negative sigma x minus sigma y sine 2 theta plus 2 plus 2 tau x y cosine 2 theta is equal to 0. From here, I can write sine 2 theta over cosine 2 theta is equal to tangent 2 theta, which is equal to tau xy divided by sigma x minus sigma y over 2. In this theta, we will have maximum or minimum normal stress, and in this theta, shear stress value will be 0, because shear stress in that orientation or that direction is equal to 0, and we will have maximum or minimum normal stress. That orientation, we will have normal stress only. Those stress we will call it principal stress. Because we will call principal stress that orientation, I will show it theta and this P, theta and this P. P stands for principal stress. So in that direction we will have maximum or minimum normal stress, and shear stress is equal to 0. So we will call it principal stress, and we will have only purely normal stress. Let's come back to the trigonometry and to see how we can find the relationship between theta P and theta S. From trigonometry, we can write tangent pi over 2 minus beta is equal to sine pi over 2 minus beta divided by cosine pi over 2 minus beta. That will be equal to cosine beta over sine beta, and that will be equal to 1 over tangent beta. So we know this. From here, if we assume, if we set beta is equal to 2 theta P, this, from here we can write tangent pi over 2 minus 2 theta P is equal to 1 over tangent 2 theta P. From here, we can write tangent 2 theta S is equal to minus 1 over tangent 2 theta P, that is equal to minus tangent pi over 2 minus 2 theta P. this will be equal to tangent to theta p minus pi over 2. Therefore, from here, we can find theta s is equal to theta p minus pi over 4. Or we can write theta p is equal to theta s plus pi over 4. So there is relation between theta s and theta p. What is that relation? Theta s is equal to theta p minus pi over 4. Okay, let's come back to that formula. Now we know what is the theta p. We will plug in the sigma theta p and we will find the maximum value for that. Again, if we have triangle, this side it is, we assume sigma x minus sigma y over 2 height tau xy, and this length is capital H, and we call this angle is 2 theta p. We can write cosine 2 theta p is equal to this length sigma x minus sigma y over H, sigma x minus sigma y over 2 divided by H, and sine 2 theta p will be equal to tau xy divided by H. Here we know sigma theta p is equal to 1 over 2 sigma x plus sigma y plus 1 over 2 sigma x minus sigma y cosine 2 theta p plus tau xy sine 2 theta p. If we plug these values here and here, so from here we can find that is equal to sigma x plus sigma y over 2 plus 1 over tau max sigma x minus sigma y over 2 squared plus tau xy squared, that is finally will be equal to sigma x plus sigma y over 2 plus tau max. This is average of normal stress in both sides of stress element, sigma x, sigma y. They call this term mean stress. So mean stress plus maximum shear stress will give us maximum normal stress. If we, instead of adding, we deduct, we will find minimum. If this is negative, we will find the minimum normal stress. So if I simplify everything here finally, if I simplify everything, I will end up with this. Tau max will be equal to square root of sigma y minus sigma x squared over 4 plus tau xy squared. Theta s, maximum shear stress angle, we call it theta s. Maximum shear stress angle will be equal to 1 over 2 inverse tangent of sigma y minus sigma x over 2 divided by tau xy. Sigma m mean stress will be equal to sigma x plus sigma y over 2. They call it mean stress. And here, if we want to draw the minimum shear stress element, minimum shear stress element will be one element like this. The orientation of that element will be theta s. In this side and this side we will have sigma m, sigma m. We will have tau max, and here we will have again sigma m, and we will have tau max, and here tau max. This will be maximum shear stress element orientation and value of the normal stress and shear stress on that element. If we want to draw the maximum and minimum normal stress or principal stress element, that element will be this will be orientation. Theta p will be equal to theta s minus 45 degree or pi over 4, and element will be in this direction. This will be sigma max, this will be sigma mean and sigma mean. In one direction we have maximum normal stress, another direction we have minimum normal stress, and shear stress on these faces is equal to 0. I think it is enough for this session. I will solve several examples. Next session I will start Moore circle. Moore circle, it is another way for stress transformations. And I will solve several examples so you will learn better. Thank you so much for watching this lecture. See you next session. Bye bye.